I think for this I'll just use the board. So in the grand scheme of things, again, kind of recap, we care about the joint distribution of a bunch of random variables. Let's say they are d-dimensional. So x maybe in R d or p-dimensional. So these are d-dimensional random variable or random vector, and we introduce the graph, right, which captures conditional independence properties, right, of this joint distribution. So how does the joint distribution what is the relation between each coordinate random variable with each other? Okay, maybe they are conditionally independent of each other given some other random variable. That's what was being captured in the graph. And then we looked at inference. So graph was just a visual aid as well as a tool to encode some metadata, which is this conditional independence properties. So that's fine. And last class we said, okay, our base object is always joint distribution. What can we do with joint distribution? We can infer. And most of the times the inference is mostly you care about marginal distributions like p of just x1, which would involve you doing integration or summation over x2 to xb of p of x1 is equal to something and x2 is equal to all these guys. You sum over all the realizations of the other random variables. This marginalization is one example of inference, and you can do this marginalization in a very interesting way rather than just doing variable elimination. I mean, in variable elimination, in my version of variable elimination, you just write this down and pass the summations inside. Okay, you can eyeball and figure out how to pass a summation inside. Maybe xd maybe this thing factorizes according to the graph. There is a way to write it as a product, right? As a product of, there'll be, for example, if it's a directed graph, there'll be one term per random variable, right? And then you can pass the summations inside, right? But for a really lot of random variables, sometimes passing by visually inspecting and passing the summations inside doesn't work. Okay, for indirect graphical models especially. So for them, we have this intermediate object called a factor graph. So for any directed or undirected graph, you could create a factor graph which would explicitly say which three or four random variables are related to each other through a factor, right? And once we drew the factor graph, then we had an inference algorithm called belief propagation, which essentially did a more clever variable elimination. Okay? Although it was passing messages back and forth on, for example, a tree structured factor graph, is essentially doing variable elimination. You can always do variable elimination as in push summations inside and get a marginal, right? But belief propagation was a way to do it more cleverly. Okay. And the second thing, so there were two things we saw in inference. One was BP, and the second thing was sampling. So sampling is also a tool for inference because you can compute functions of distributions, functions of joint distribution. This is a function of a joint distribution because it's the joint distribution object is there, you do a summation, right? Other functions of a joint distribution you can think of are expectation. Expectation is a function of a joint distribution because it's just a whole summation with the joint distribution times the random variable, for example, right? So such functions can be computation of such functions is called inference, and another way to do inference is to do just sampling. Okay, you sample a bunch of points from this, ideally from this joint distribution, and then take an average, for example. That will let you infer the expectation of the random vector over this joint distribution in an approximate way. Okay. Now, within sampling, there was a technique. I mean, so the version that I just mentioned, get samples from p of x. It may be easy or hard. If it's easy, you just get one sample. Maybe p of x is just a multidimensional Gaussian, in which case there is a although we will not study how to sample from Gaussians, there is a simple way to do it. Okay, relatively straightforward way to do it, and you can get maybe 1,000 samples, take an average of each of the Gaussian vector realizations, take an average. Okay, but sometimes this distribution is not just a Gaussian, right? That's the whole point of having having graphical models. Each random variable may have different conditionals, different marginals. They can be some can be binary, some can be discrete, some can be continuous, and so on. So it can be a mismatch of all these distributions. So in that case, you can't really sample independently. And so there was this whole set of techniques which were called Markov Chain Monte Carlo methods, which can generate samples, little x, little x1 to little xn. It can generate these samples, but these samples are dependent. Okay, that's why this the Markov chain part of it. The samples are going to be dependent, but still these samples are such that eventually, it's a procedure which is iterative. It's a sequential procedure. You'll get, you'll get these samples. Let's say you ignore the first 1,000 or first 10,000. Then these samples essentially look as if they were drawn from. If you just draw a histogram of these guys, they look as if they're drawn from P of x. Okay, that's the idea with Markov chain Monte Carlo. Ultimately you want to get samples from here so as to compute averages and so on. You can't get directly samples from here. You'll create a method which will create some samples in a way, and I'm going to describe give sampling in this context again, repeated. But you'll get the samples, and the samples have the property that, of course, they're dependent, but if you just draw a histogram of them, eventually they'll look like, the histogram will kind of look like P of x itself. So it's as good as saying the samples are from P of x. And I'll make it a little bit more precise today. Any questions about this lay of the land? And why are we studying joint distributions? You remember Gaussian, Gaussian mixture models, hidden Markov models. Today also we'll see LDA, which is a very famous topic modeling technique for text analysis, conditional random fields, and so on. So there are many methods. So outside of deep learning, you might have seen SVMs and random forests and so on. But beyond that, so this really, is the right object to look at when you have more interesting applications. Right? Okay. When you can't apply random forest, you can think of a graphical model and then try to do inference or learn and so on. Okay. So what is the Markov chain? The object, last time I said there is a the whole point of Markov chain method is Markov chain Monte Carlo method is to create something called a Markov chain. What is a Markov chain? Okay, so let me describe a Markov chain using a small example so that it's more clearer. So let's say there are two random variables only. Okay, this is I'm thinking of the fly. So let's say x1 and x2, and x1 takes two values 0 and 1. X2 takes three values. Let's say. 1, 2, and 3. Okay, let me same numbers. Okay, 3, 4, and 5, and this takes 3, 4, and 5. So, in a sense, x2 takes these three values, x1 takes two values. So, all the possible pairs are these, right? 6 pairs, right? 6 possible values that they can take, and you would ideally write, p of x1 is equal to something, and p of x2 is equal to something else. You would ideally, think of a table like this, which would be a joint distribution. There is some numbers, they add up to 1, right? Now, what would a Markov chain be? So what would a Markov chain method do? Would be as follows. We will consider each realization as, they call it a state. Okay. So think of each of these realizations as a state. Okay. There are 6 states in this for this example. Okay, so there's 6 states. So just draw 6 blobs, and what would a Markov chain method do? Would describe what is called this Q object that I was talking about last time. Q, right? This is object Q. I think I was using a notation x2, x hat or something, but basically this is an object. Okay, what is this object? This object is basically saying how do I go from a state to a state. Okay. What does it mean to go from a state to state? Let's say you are at state x. Okay, maybe I should not use capitals. Okay, I'm going to use capitals, abuse of notation, but let's say you're in state x. It just tells you what is the probability of me going to another state x prime. Okay, and in the sense it's a probability, so I can go to any of the states. Okay, maybe from this state I can go to any of the other other 5 states. Okay, so Q just tells me what is the probability that I go into a specific state, maybe from 0, 3. This one is 0, 3. What is the probability I go to 0, 4? What's the probability I go to 0, 5? 1, 3, 1, 4, and 1, 5. Q tells me that's the object. It's called a translation probability function or translation probability matrix. What do you think of the different names for this guy? Are you guys able to see? Any questions at this part? So Q just defines from a given state go to some other state. What is the probability of going to some other state? Okay, and maybe it with some probabilities goes to the same state. It stays in the same state. Okay. So saying it's a basically conditional probability. Condition on X, which is a given state. What's the probability I go into some other state, including myself? Okay. It's a conditional probability distribution. Okay. It's so Q essentially is kind of corresponds to a Markov chain. The name Markov chain and this Q function or transition probability are kind of synonymous. There is a lot of theory behind Markov chain and so on, but for us, we'll kind of not think about many of these other properties and just think of Q as a transition probability matrix, which kind of tells you how do you go from state to state. Okay. And why do we care about this Q? Is because this is a conditional probability. Okay. And what happens is in a Markov chain, you can jump from one state to the other using this Q function, right? It tells you if you are here, it tells you to go somewhere else with some probability. You go there with some probability. From there, it tells you go to some other location with some probability. You go there with some probability. That's like actually going from one realization to another. Okay. So just using Q, you can keep generating samples or realizations of your joint distribution, except that they are dependent because Q is a conditional probability. Depends on where you started from to go to something else, right? So that's the Markov property. Markov property just means things are dependent, but in a nice way, that it only depends on where were you before, not where were you 2 steps before, where were you 10 steps before, doesn't matter. Okay. So that's it. So Markov chain is essentially using the Q to jump around on states. And a nice property about Markov chains, which is that there is something called a stationary distribution. Okay. There's going to be something called stationary distribution. I think I don't know what notation I use. I think I use pi. So Q is the only object. Given Q, I can compute something called pi. Okay. So Q is completely determines Markov chain. I'm telling you that if there is a Markov chain, there is some other computed quantity that I can derive, which is pi of x, which is called a stationary distribution. Okay. And what is the stationary distribution? It's as the name suggests, something about things not changing. Stationary just means things not changing. It's a distribution. So it's a distribution over x, which means that it's like p of x. Okay. So p of x is a distribution over x, random variable, x random vector. Pi is also a distribution over x random vector. This thing has a special property that pi of x is equal to sum over x x prime all the other states. So all the states including maybe itself of pi of x prime times q of x prime to x. Okay. So pi is some distribution, which is essentially a bunch of these numbers, right? That's what a distribution is. The distribution satisfies this some sort of linear equation, which involves q. So q is the only object which can completely satisfies Markov chain. Given q, I can potentially compute pi, and sometimes you cannot compute, but let's not worry about it. Things we can compute pi in some nice cases, and pi is called a stationary distribution. It's basically saying if I was in state x, if pi is a distribution such that if I have a distribution over my over my states, as in over my realizations of my random variable, which is pi, then the probability that I'll end up in a state x is just pi, right? So with pi of x prime, I start, there will be a pi which is essentially a number for each of these circles, right? Each of these nodes. So think of it this way: I'm in each of these nodes with probability pi of x prime, and with probability q of x prime to x, I jump to x, right? So this is the probability of jumping to x, total probability, right, over all the x primes. That is just equal to pi of x. Okay, it satisfies this equation. That's how a stationary distribution is. Any questions? Yeah.
So final input will be the same, like final state and input state is same. Then it's stationary distribution, right? For example, 0,3 in that diagram.
So one of these x's can be 0,3. X prime can be 0,3, 0,4, 0,5. 1,3, 1,4, 1,5. So basically there are 6 numbers. Any pi in this example has to have 6 numbers. Any distribution will have 6 numbers, right? Pi is a special distribution. It's called stationary distribution because it satisfies this equation. Q is fixed. Q is a thing that I'm describing to numbers of how to go from one state to the other. So given a Q, there is a pi, and the pi satisfies this equation.
So in this diagram, only 0,3 will be satisfying this condition, right?
No. I just drew one example. I mean, there will be arcs from everything to everything, and there will be equation for every x. There will be an equation like this. So for all x, actually, for all x. So in this case, for all 6 nodes or states here, for all 6 nodes, there will be an equation like this, which is satisfied by a single pi. So it's like a bunch of linear equations. There will be 6 such linear equations. Linear equations because think of pi as like an unknown thing. If it was unknown, you have a bunch of linear equations describing what that pi is. Okay. I think that's what's written in the notes somewhere. Okay, so this equation here, I think now what I wrote there has a little bit of an expanded fine, but otherwise, so there is a station. So given a Q object, there's a pi, okay, and so stationarity just means that as you kind of keep jumping from state to state, eventually you will see that eventually me seeing a state is as good as saying I'm sampling from the stationary distribution. Okay. Because eventually I will have realizations coming from the stationary distribution. Because let's say there's a distribution over these states, which is pi. Okay. Then the probability that I'll see the next sample that I see is just going to be from pi. Okay. That's essentially the interpretation of this equation. If I start from pi, I'll end up with a sample from pi itself, because because Q is fixed. If I started with pi's, I'll end up getting a sample which is according to pi itself. That's what this means. So once you internalize that there is this object that can be derived given a Q, so somebody has to tell you Q, and given Q there may be a pi. Okay, it's not always the case, but let's say there's a pi. Why did I introduce pi? Is because I want to kind of reiterate the interpretation of pi. Pi is essentially like eventually I keep jumping according to this Q, which is transition probability. I'll get these x's, realizations x's. Eventually a new sample essentially looks like being drawn from pi only. Okay, that's what it means to be stationary in the sense there is a single fixed distribution. The new samples appear as if they are coming from a single fixed distribution pi of x. Even though I'm jumping around according to Q, I'll get a new observation from essentially pi of x because pi of x satisfies this recursive equation. Okay. This is true for? No. this is only a fact. This is only related to Q. You know, Q is what you need to specify. Yeah. Yeah.
Is it true for any multivariate?
What does it mean? So if I specify Q, you can tell me whether there is a pi or not.
We need to find Q, right?
No, we don't find Q. We design Q. So given a Q, you can ask a question whether, you know, does this Q have a pi or not? That's all. Your question is whether for any multivariate distribution there is a pi. That's not a right question, right? What does it mean? My only object is transition probability matrix. Transition probability function. So given Q, I can tell you whether pi is there or not. If there is a pi, maybe there's a way to compute it. In fact, there's a way to compute it, which is solve this bunch of linear equations, substitute pi's as unknowns. You'll have one equation per state or per node. I solve it, it will get a pi potentially.
What I'm saying, we have two assumptions. We are saying that let's take a Q and
Yeah.
that will find if pi exists or not.
Given a Q, I'll give you a pi.
It will give you a pi.
Yeah.
But there's another assumption that where Q exists for a given distribution.
What is meant by Q exists? I design it. I can always design. If I know the realizations, I can tell you, okay, I can say, okay, from 0, 3 with probability 1, I'll go to 0, 4. That I design it. What do you mean by whether it exists or not? Right? I can define it. I have to define something, which is Q. I can define it in a way. So it's by definition exists. Okay. Whether it's an interesting one or not, it will be interesting. Okay, that's the final thing, you know, wrapping it up. Final thing is, this is going to be interesting if this pi happens to be P of X. Okay. So it's a very P of X here. So the whole point of Markov Chain Monte Carlo methods is to design Q, as in think of jumping from realizations to realizations, and that's how we get a bunch of realizations, right? Sequence of realizations. And the Q is such that its stationary distribution is just P of X. Okay. And why do we care about you know, designing a nice Q such that its stationary distribution is P of X? Is because if P of X is a stationary distribution, our samples will look like as if we are being just drawn from P of X, although we are just jumping around according to Q only. Jumping around states, jumping around realizations only according to this conditional probability. Our samples will look as if they are coming from P of X. Okay. That's the idea. So okay, and actually, so and you can actually check whether, so if somebody gives you a Q, whether the Q has a you know, has a P of X, I mean, has a P of X or not, you can check with something called detailed balance equation. Okay, which just means that P of X or whatever, pi of X times the probability of me being in some state or some node X. Okay, like for example 0, 3. From 0, 3, probability of going to, let's say, 1, 5 is the same as probability of me being in 1, 5 times the probability of me going from 1, 5 to 0, 3. If there is a pi which satisfies this, then it is stationary. Okay, it's something like, if this is true, then it's a stationary distribution. Okay. Otherwise, you just solve this, and if you get a unique solution, you're fine. Okay. But you solve this, you have to solve a bunch of equations, one per every state, and that can be too many. And the reason why we kind of mentioned this detailed balance here is that we can actually see that Gibbs sampling is, you know, Gibbs sampling essentially corresponds to a Q. Okay. I'll tell you again, recap what Q is for Gibbs sampling, but Gibbs sampling essentially corresponds to some Q, and if you kind of study, you know, put that Q into the detailed balance equation, you'll see that pi of X times Q of X to X prime is the same as pi of X prime to times Q of X prime to X. Okay? That the detailed balance equation holds for Gibbs sampling. Now what does Gibbs sampling do, if you remember, is essentially going from one sample, let's say x1, all the way to x1, all the way to x2, right? So x1, for example, in that case is two-dimensional, let's say 0, 3, and x2 I don't know. Okay, this is a, you know, I have to jump according to Q, right? So Gibbs sampling, what it does is it first says, okay, draw x2 1, the first coordinate of x2 according to the conditional probability of you know, that first you know, conditional probability of the first coordinate. use x1. Given the other coordinate, right, x2 is this guy 3. Right, git sampling is always doing one. It's picking one coordinate and saying all the other coordinates I'll either remember from the previous sample, or if I have already sampled them, I'll just remember them. Okay, you get one sample, and then you get the second coordinate of the, maybe this is equal to 1. Okay, let's say this is equal to 1. x21 is 1. Then you filled in one number here for the new sample, and the second sample you'll get by drawing according to a conditional distribution again, x2 given x1 is equal to, let's say, 1, okay, whatever the number this was. Right. Maybe this is equal to 5. Okay. So this is how you get samples. These two steps correspond to a queue. Okay. I mean, queue is basically saying going from one sample to one sample, right? But in git sampling, there's a bunch of sequential steps. Per coordinate, there is some sampling involved. But overall, it binds them together. There is a going from one previous sample to another next sample, right? That's so you can check that git sampling does basically satisfies detailed balance. So this you should just check using, in as homework. Yeah, I think. Yeah, and for others we don't really talk about much, but there are some other ways to also go from x to x prime. Okay. Again, this is some other queue design. These are called metropolis testing methods. Okay. These are also Markov chain Monte Carlo techniques. They specify different Markov chain going from x to x prime for every x to x, every x to x prime, and they require defining. They require evaluating P and having some, fake, you create some transition probability distribution. Q design. Right? I mean, here also it's not out of the hat that we defined this conditional probability. This conditional probability is related to P of x, and that's why somehow for this Q, the stationary distribution is P of x, because Q is designed using P of x roughly. Right? It's not unrelated. Okay, any questions about this part before we move on to today's topic?
So x1 should be 0, right?
No.
Not 1.
First sample, let's say I've already started with one sample, which is essentially 0,3. Let's say I started with 0,3. Or maybe it's something else. No, it's 0,3 here. Yeah. You want me to change this to something else?
So in the third step,
this step?
Yeah. So x1 should be 0, right?
X1 is, I've already realized X1. No, I'm constructing the second sample, right? I already have X1, so I don't have to consider the previous sample's coordinate. I've already realized the first coordinate of this new sample, so I'm just using the newest, freshest value, most recent value. Okay. If I did not have this, I would consider the previous. I mean, if there were 3 coordinates or something, you would kind of see that. Yeah, you had a question?
So as we keep jumping states, is it important to keep a note of the points in which we have been which the point has covered historically?
No, you don't have to keep any nice track of them, which ones you have covered, but you just remember those samples, because those are essentially your Monte Carlo samples, which are dependent, but they are essentially as good as sampling from P of x.
Yeah. So at the end, are we trying to find out which path has the way it?
No. How we are jumping around doesn't matter. We don't care. We just want a sequence of samples. Ideally, we want a sequence of samples from P of x. The whole difficulty is we can't directly get something from here, so that's why we are constructing this proxy object and getting samples.
Yeah,
okay.
So
we don't care about the exact path.
Yeah. So are we trying to finally figure out which path? I mean, as we keep changing states,
yeah.
the final point that we reach. Are we trying to find out?
Yeah, the
which
final
is
point.
the best probability.
Yeah, the probability with which xn happens is actually pi of x eventually, and pi of x is nothing but P of x for give sampling. Yeah. But we are not trying to find we are not trying to remember the path or with what probability an x is happening. I mean, eventually each new sample realizes according to the stationary distribution, and that is equal to P of x. Although we are jumping around and using Q.
So shouldn't that be important
So to remember the path, it's not important. Why should it be important?
I mean, because if you know that this is the best way that you can travel from one, initial point to the end.
No. Here it's all stochastic, right? We're jumping around by flipping coins.
Yeah.
So there's and also it's Markov. Once you are in a certain position and you jump to another position, if you jump to some new position, the only previous position matters. The whole path doesn't matter. Yeah. It doesn't matter in this model.
But taking a note of which is the best path.
What is the best path, right? So best means there is a one non-stochastic thing. It's not necessary here. I mean, maybe in some other application, some other context, maybe you want to remember. So this essentially talks about jumping around a graph. You can think about paths and graphs and so on, but in this sampling application, at least in Gibbs sampling and metropolis hasting, it's not consequential. Okay. Any other questions? Okay, so today we'll start with something else. I don't know. Okay, so this recap slides are from same as previous lectures. Basically, we have seen unstructured data, or structured data, beyond random forest and what is this, SVMs and stuff. Graphical models are the more interesting, more expressive and flexible models. Okay. And in terms of the three parts that we are looking at, I started with some applications and then described that a graph can capture conditional independence properties. That's the metadata, which are what I call metadata. And then last lecture was all about inference, how to compute things like this. And then MCMC methods, it looks like it's not related to inference, but once you get samples, you can compute. Once you get samples, you can just look at the first coordinate, and that essentially gives you P of x1, right? Or you can compute expectations, averaging. Once you have samples, you can average things. Today we'll look at how to get the parameters of the distribution. So this is something that we kind of glossed over, which is that P of x will have parameters, right? First of all, if there is no explicit, if there is no graph, or the graph is a complete graph. So let's say in this case, x1 and x2. This is a very simple case, but let's say x1 and x2 independent. Okay, then x1 takes two values, which means that you need two parameters or one parameter for x1, and x2 takes three values, then you need three parameters or two parameters for x2, and that would be enough. Okay, right? If they were independent, but if they're dependent, you need 6 numbers or 5 numbers essentially here, right? So these 6 numbers are essentially the parameters of this model. In the sense this joint distribution. Okay, that's what I mean by parameters. For Gaussian distribution, for example, the mean and the variance or the covariance matrix is going to be the parameter, right? And so today we'll see how to learn parameters using data. So this is where so given data, how to get the parameters, and we'll see that we'll revisit some of the topics that you've probably seen multiple times, called maximum likelihood estimation, and maybe even expectation maximization. Okay. Okay. So let me just kind of recap some of the applications. So we looked at hidden Markov models. I'm going to kind of spend a few more minutes on hidden Markov models just to kind of tell you what the model is again. Then Gaussian mixture models, at least people who took 575 should remember a little bit about Gaussian mixture models. People who did not take it, we'll kind of revisit it again. It can be useful for clustering. Okay, so clustering, you've seen k-means, right? K-means has something to do with Gaussian mixture models and EM algorithm. Maybe we'll just kind of remark on it towards when we get there. So LDA is also a graphical model, right, for topic modeling. We'll try. I don't think we'll get to see how do you learn parameters of LDA, because it kind of mixes two concepts. One is EM and the other one is variational inference. So if you remember variational autoencoders, there was this KL divergence and stuff, right? So maybe we'll not look at learning for LDA, but LDA is also a popular application. Okay, and conditional random fields again are some nice extensions of nice applications of undirected graphical models. Okay, so these, I guess the first three you can call them maybe directed. Okay, so okay, let me actually get to. Let me skip that because I'll again revisit it anyway. That's hidden Markov model anyway. So let's say, I mean, so just to motivate, like what are we trying to say? Let's say there is a PDC network which essentially is a directed probabilistic graphical model, right? Let's say there are 4 variables: cold, allergy, C and A, and then some H, I for cough and itchy eyes. Okay. Now, I mean, there's a corresponding factor graph and stuff that is fine. And so let's say you observe 2 of the random variables. In this case, in this world, everything is a random variable. You observe something that's going to be a random variable. So you're coughing and you have itchy eyes. So let's say those are the 2 realizations of the 2 nodes here. So given that, can you tell me what is the probability of C? Can you tell me what is the probability of A? Okay. If maybe probability of A is high, then maybe we can say allergy was the issue. If the probability of C is high, you can say maybe cold is the issue. Okay. Is that kind of clear? And how do you say that? There's a conditional probability, right? Condition on H is equal to coughing and I is equal to itchy eyes. Tell me what is the probability of C. That's the conditional probability computation, which is actually inference. So you can use PP, or you can just do variable elimination in this case because it's a small graph. Any questions about this example? So everybody understands this, right? Okay. So I mean, same type of, in a similar pattern. In this case, I'm actually showing you the realizations of these 3 random variables. In this here, there are 6 random variables. So 3 potential disease conditions and 3 measurable things. Okay. And here I'm saying, so the measurable things are in gray, and I'm saying, fever, no fever, cough, no cough, vomit, no vomit. And so these are binary random variables. And 1, 1, 0 just represents the state in the sense of one realization that you've seen. And somebody has already told you this graph, and somebody's already today's lecture is all about how to learn the parameters of this graph. But given this realization, maybe you can find what is the probability of, let's say, 1, 0, 0. That would be a conditional probability computation. Okay. And there's a way to write this, right? For each these. So when you look at this graph, the way you can think of how did these realizations happen is for each disease condition, you generate an activity of the disease, whether it is present or not. Maybe 1, 0, 0 was the sequence of numbers that you got here, DIs. Okay. And then for each symptom, you just find the probability of that symptom given that I've realized 1, 0, 0. Okay. That could be, draw a sample for each of these guys, and it happened to be 1, 0, 1, 1, 0. That's just a way to describe, from parents to children, how things can realize. Okay. So let's kind of spend a couple of minutes on hidden Markov model. It's a nice time series model. It's also related to something called Kalman filter. Both are essentially Markov models. Kalman filter works for continuous numbers, so things, random variables which are like continuous. Hidden Markov model is also, is also related, but not specifically for continuous random variables. So Kalman filter assumes some Gaussian assumptions. Okay, everywhere. Here there's not necessarily any Gaussian assumption. Okay, so we'll see what hidden Markov models are. So here, HMMs are essentially, sequence of random variables. Sequence of, there will be 2 sequences, bunches of H's and bunch of E's. Okay, so the model is essentially a sequence of random variables. You can stop it at some time, or you can keep on going. Whatever, it doesn't matter. And the connection between the random variables is going to be like this, nice structured way. Okay. it's as good as saying if I remove the bottom, variables, essentially like a chain, one leading to the other, leading to the other, leading to the other, and so on. Okay. And so let's motivate the applied problem of object tracking. So here, hi, maybe there are k such random variables, and let's say hi represents the location of an object at time step I. So maybe h3 is 2, 3. Maybe in grid 2, 3 on a 2D grid, the object is present. And E's represent the sensor reading at time step I. Okay. So the sensor can maybe is not measuring exactly where the object is. Maybe it's just measuring the sum of the coordinates of the object. Maybe h3 is 2, 3. Maybe E3 is saying it's 5. Okay. Some measurement is 5. Okay. Maybe the sum of the individual coordinates. So the description of the model is you start with some distribution over where the object could be. Okay. If it's on a 2D grid, maybe you don't know where the object is. Maybe it's uniform distribution. So maybe if the 2D grid has 5 cross 5 cells, which means 25 cells, then each probability of being in any grid is 1 by 25. That's it. Okay. Then there is this. If you think of the directed probabilistic graphical model, each node only depends on its parents, right? The parent of H3 is just H2, and the parent of H2 is just H1. Okay, and H1 doesn't have a parent, so that's why I explicitly said what the P of H. So remember in directed probabilistic graphical model, each variable will have a term or a factor, right? So here the factor for H3 will be H3 given H2, or H2 will be H2 given H1. Okay, so that's the transition. And here we are just saying that given in a location, you can probably only go one step forward or one step backward or something like that. Okay. And these random variables are related to just mirror these first sequence of random variables, and these are considered I guess observable random variables, such that they are in gray, and these are white, and these are hidden random variables. In the sense, these are latent variables. Okay. You don't observe them where the actual object is, you only make measurements, and these measurements are observed, so that's why they are in gray. And these measurements are essentially based on where the object is. They only depend on where the object is. Okay, that's why the parent of E3 is just H3. Okay, so the factor corresponding to EI will be just P of EI given its parent, which is HI. Okay. And this may have some noisy model, which is uniform over. Maybe if it's exactly 2, 3. Because of measurement errors, you are probably not off. You may be off by a little. Okay. Let's see. So, what is the description of this model? Is as follows: for each time, you generate an object location, which is going to be given the previous location. Where can I go next? Okay. Right. That's because given the parent, what can I do? What value can I take? And then, given what value I took, what would be a sensor measurement? Okay, that's the description, and this is where the time series aspect comes in. Okay, so given the previous value of where your stock price is, what could be where the next stock price can be? Any time series forecasting setting can be captured here. Okay, if it's Markov in nature, it only depends on the previous values realized in the previous 1 time or 10 time periods and stuff like that. That can be captured. So here I'm just saying if I'm 3, 1, maybe there's some probability with which I'm going to go to 3, 2, and if I'm in 3, 1, maybe my measurement is just the sum. Maybe it's a deterministic measurement. It's just the sum of the 2 coordinates. Okay, maybe my measurement is 4, 5. And to write down the joint distribution explicitly, okay, that you can. By just looking at this graph, you should be able to write the joint distribution, right? It's going to be, this guy doesn't have any parents, so P of H1. Each of these guys have one parent, that's P of HI given HI minus 1, right? And then each of these guys have one parent, so P of EI given HI, right? So this is the joint distribution of all these random variables. Okay. And inference problems in this model, okay, if you had figured out the parameters, let's say you had data from which, this is the graph that you want to fit, you somehow fit the parameters of this data. Now, given the data, given the fixed parameters, you want to find what is the probability of H3. Okay, because you don't observe this, right? You don't observe this. You have figured out the parameters of this transition length. Okay, this probability is what you figured out. Now, you can find, given my observation that I made observation of 4, 5, something else, 6, let's say, what is the probability that the object is in some location? You can actually, this is an inference problem. Okay. And same thing with something called smoothing. Smoothing just means you kind of look at future observations as well before you find. Doesn't matter. So I'm giving you 2 examples of inference problems. If you had this type of a time series model. In particular, I mean, so now in terms of learning, you have to learn these transition probabilities, right? These probabilities, and what we'll do is say that, okay, it doesn't matter what the random variable is. I'm going to use the same transition probability function. Okay, this is one big difference from what the previous slide, and it doesn't matter whether from H4 and E4 depends on H4, E3 depends on H3, E2 depends on H2. These are different random variables, but they all follow the same probability rule, and that's going to be probability of emitting of EI given HI. So there is some fixed, these are not indexed by I, so these are functions which given previous in this case you can call this a state, given where will you go, and that doesn't depend on I. Okay, so you kind of can learn these two using data. So in this case, parameters would be, tell me how do you go from one hidden state to another, and tell me how, given hidden state, what values can you take. That's these two probabilities, conditional probabilities.
So this is an assumption you're making on the data, or is it?
Yeah, this is an assumption. Yeah, in this model, it's an assumption. Otherwise, these are different random variables. You have different things to compute, different conditional probabilities to compute. Here we are making an assumption. Yeah. So we only have 2 conditional probabilities to compute.
Maybe don't have H1.
H1 is missing. Yes, it has to be H1. I mean, that's why the title is, I guess, parameter sharing, and we'll come back to this idea again. So parameter sharing just means these conditional probabilities are not unique for every pair of random variables. These are common across pairs of random variables. Okay. I mean, I've discussed HMMs and so on in the first lecture, in the 2 lectures before, but I'm revisiting them. So you should, if you have questions from there, you should definitely ask now, because it's the second time we're repeating it. So if you miss this chance, then it's going to be like at the exam you'll see this and then like, what is this, right? Okay, so let's look at Gaussian mixture model. Where is it? Yeah, I mean here it's really not saying much. This is the just a definition of a multidimensional Gaussian. We don't have to remember that actually. So what is a Gaussian mixture model? It's a mixture of Gaussians. Mixture of Gaussians just means, let's say we have k Gaussians with means mu k and sigma k. We also need another object which is going to be theta, which is going to tell you what is the probability of being in any of these, being in any of these components. So there are k components. Each component is going to be Gaussian, okay? And theta is just saying which component your observation came from, essentially. So the mixture model description is as follows. Okay. The mixture model says first you draw a sample from theta. So theta is a categorical distribution or a multinomial distribution. It's the same thing. It's basically saying, so think of it this way, right? Theta is just a PMF. Let's say k is 4. Okay, k is 4. The little k over there is 4. Then theta is essentially a distribution like this, PMF, right? You draw a sample from here. Maybe it's number 3. Okay, that is y here. So this is theta. So you draw y, and maybe y happens to be 3. Then you draw a sample x, which is actually from the third Gaussian. That's all. So that's what you observe is just the Gaussian realizations, only x's. But you're hypothesizing that the way these x's came about is first you're choosing one of the Gaussians and drawing a sample from the Gaussian. Okay, and there are a couple of pictures to illustrate that in 1 and 2 dimensions. with two components. So here k is equal to 2. So we have two Gaussians here. There's a red one and there's a blue one. And the data, maybe, so let's ignore the red and blue first. Let's say you had data, one-dimensional data. You have a bunch of observations, bunch of numbers. You drew a histogram, and the histogram looked like had two modes. It's bimodal. Okay, it has two peaks. Okay. Now, by looking at two peaks, maybe you can hypothesize that maybe it's a mixture of two Gaussians. And then you're saying, can you estimate? Once I say it's a mixture of two Gaussians, I've completely specified the joint distribution, which is that with some probability I'll pick one of the Gaussians, and once I pick that Gaussian, I'm going to sample from that Gaussian. Okay. So you need to estimate the mean and variance of the red one, mean and variance of the blue one, and also the proportion with which you're going to pick from the red or from the blue. Okay. Those are the parameters of the model. Same thing with this two-dimensional distribution. So let's say again you had some bunch of points, and the points look like they are two clusters. Okay. Then what you'll do is, okay, maybe I can hypothesize two-dimensionally. You can just visualize. So hypothesize that it's a mixture of two Gaussians. Then it looks like from eyeballing, maybe they have the same variance. So I just need to figure out the mean of this Gaussian, the mean of this Gaussian, and the proportion with which I pick from one Gaussian or the other, and maybe I can fix the variance to be the same. That's just modeling choice. And you can see that it can be used for clustering, right? I mean, any new point, you just figure out what is the distance from the closest mean, and maybe it belongs to that Gaussian, that cluster. Okay. And how do you learn a Gaussian mixture model? And this is where the EM algorithm comes in. I'm going to describe EM again in detail, so let me skip this. But this is the overall intuition is, actually HMMs and GMMs, what you don't observe. So here, in GMMs, you don't observe Y's, you observe X's, bunch of samples. In the 1D case, you observe X's, right? But you're hypothesizing there are two Gaussian, and so there has to be this proportion, with some probability you'll pick the first Gaussian, with some probability you'll pick the second Gaussian. You don't observe these random variables. Okay, there's one random variable per observation that you don't observe. Okay, so and in the HMM case also it's the same, right? You observe this sequence, and you're hypothesizing that there is a hidden sequence like this from which I'm getting E's, but you don't observe H's. So how do you learn? So how do you infer? Where is it? Yeah. I mean, okay. Let's not worry about inference. So how do you learn the parameters of this model? There is a speed transition and P emission. Let's say. How do you learn these numbers? You're going to use, if you had observed everything, you can just use maximum likelihood estimation, and we'll see this concept in few slides. I'm just kind of saying, giving a preview. You can just use maximum likelihood estimation for any bunch of random variables if you observed all of them together. But since you don't observe the H's, you can do it in an EM way. So for both HMMs and Gaussian mixture models, what do you actually do? And it's summarized in summarized in this slide. It says compute expected values of unobserved variables. So in HMMs, unobserved variables are H's. So compute what could those values have taken, right? Assuming some current parameter value. So you start with some parameters, P transition, P emit, or in Gaussian mixture model case, some mu, some variance, some proportion. Start with something, some parameters, initial candidates. Compute what could have these unobserved variables taken. And then once you have this, because I know what, I have an estimate of what these hidden variables have taken, given that now I can maximize what is called likelihood, the likelihood of the whole data, both the observed and the unobserved. Unobserved, I have an estimate of what they could have taken. So because I have the estimates, I can, given those two, I can now update, can get new parameter values. You kind of repeat this over and over and over.
What is the last information? Initialize expected values. Isn't that the same as first one? Is there a difference?
Initial expected values, ignoring. Okay, so We'll come to this when I have an example. I have an example in a few slides. You'll get that. Okay, and so this has to be a recap for 575 people. Okay, and people who have not seen 575, I'm gonna maybe not for this example, but we'll actually look at EM in more detail. But for 575, who have taken 575, okay, the previous concept that I just explained, we observe, let's say, x's. Okay, x's are these, the one-dimensional case, the observations, the real numbers. For each observation, I'm gonna say what is the probability of y. Y is, there were only two Gaussians, right? So y can only be first Gaussian or second Gaussian. So essentially, y is a binary random variable. So I'm saying what is the probability of y for each xk. Okay. So think of mu I is, actually the notation has changed, but think of mu I as y is equal to 1 and then y is equal to 2. Let's say there are two Gaussians, right? What is the probability of y is equal to 1 given x point? What is the probability of y is equal to 2 given x point? Why can I compute this? Because I have a current estimate of parameters. Current estimate of parameters include mean and variance of the first Gaussian, mean and variance of the second Gaussian, and the proportion. Given that joint distribution, that completely specifies the joint distribution, I can always compute all sorts of conditional distributions, right? Inference. So I can compute this. Okay. So do this for every example. For example, hypothesize what the y could be. Okay. And once you get those numbers, and that's just a simple inference problem. If you knew what values y could take, then in the M set, if you actually solve the maximum likelihood estimation problem of both the x's and y's, you will see that, you'll just write an objective, which is the likelihood, log likelihood, maximize it, take the derivatives, first derivative set it equal to 0, and all that. You'll see that you'll get you'll get new parameter values. Okay. So what are these mu's? These are new parameter values, new means of the two Gaussians, new variances of the two Gaussians, and proportion. What is probably y, just y is equal to 1 and y is equal to 2. These are the update equations. So let me come back to this at the end if I have time, because I can explain this, but let me go to the simpler EM example, which people who have not done 575 will see first, and then we'll get back to this. Okay. Any questions? For those who have seen 575, if you have any questions. Do you remember EM from 575? Okay. But for those who have not seen, I want to describe EM on a simpler example with numbers, so you can actually understand what's going on here. It's just formulas for one-dimensional Gaussian, which you can derive, but let's not do it in real time. Okay, so that was HMMs and GMMs. Okay, and in fact, I was telling that HMMs and GMMs were the state of the art for speech recognition till 2010, let's say. Yeah. There's an open source project called CMU Strings, which essentially still has HMM and GMMs because they are so well fine-tuned and can do speech recognition compared to like a deep learning based method, unless you are, let's say, Google or Facebook or one of these companies, right? Okay, so the third model is LDA. So LDA also I've kind of described previously. It's a model for hypothesizing topics of documents. So the only thing you observe is documents, bunch of documents, right? But given a bunch of documents, you can kind of infer something about what is their topics composition. So what are topics? They are just hypothetical objects. In fact, topics specifically are just a distribution of our words. Okay. So we'll do topic modeling, and the purpose of topic modeling is maybe once you kind of have a model using given bunch of documents, somehow have a model which involves topics. Given that joint distribution, the model essentially is joint distribution. Given the joint distribution, given a new document would be conditioning on some observed variables. You can tell what the probability of unobserved variables is, in this case topics, and you can say what topic the document has. Okay. So that's the kind of flow, higher level workflow. Okay. Given document, somehow compress that into a joint distribution, and given the joint distribution, given new evidence, which is new document, tell me what the topics are. And does anybody recall how LDA works? I think I asked this question even 2 weeks ago. but 3 weeks ago. But anyway, so the starting point is, so most joint distributions, graphical models can be described in a, or at least the directed graphical models can be described in a very stage-wise sequential way. First, you generate a multinomial distribution, or to be more accurate, it should be a categorical distribution. It's the same. It's categorical. When I say the categorical distribution is just a probability mass function. Okay. If you have 3 topics, then theta is 3-dimensional with one number. Probability of sports topic is equal to 0.3. Probability of stock market is 0.4. Something else, books is 0.3. Something like that. Okay. That's what it is. First, you generate a theta. So it involves some parameter. You'll have to learn the parameter eventually, but you generate a theta. Okay. So theta is actually a hidden variable. Okay. Although it's a distribution, okay, because you're drawing it randomly, it's a random object. So it's a random variable. It's a hidden variable. Okay. Now, given theta, so theta. Okay. Okay, so given a theta, which is the distribution of topics, let's say the document has n words. For each word you'll first generate a topic. Okay, for each word you generate a topic. Maybe the first word is topic sports, the second word is topic books, the third word is topic sports again, fourth word is topic stock market or something. Then, since I know the topic for each word, I'll go to my topic. Since I know the topic is, as I said, is a distribution of words. Since I know the topic, I'll generate an actual candidate realization word for each location, each word, by just drawing from the topic. Okay, it's a distribution, and so there has to be a topic-specific distribution, which is theta. So for every topic, let's say there are 3 topics, so there will be 3 beta vectors over my vocabulary, and I'll just draw a word from each topic. Okay, that's a generative description of the topic model. And any questions about how the topic model generative description is there? Okay. Let's not skip all this. Okay, this is not needed. Now, so kind of, I think last time Mrinal, I think, asked a question about why does LDM work, right? Why do we get different topics, right? So if you actually think of it, think of the joint distribution P of, you have to think of what are the random variables here. Random variables theta, the z vector, and w vector. Let's say for a single document. So a bunch of words that you realize that you actually observe, bunch of topics that you realize per word that you don't observe. Theta is something that you don't observe, right? Given alpha and beta. And beta is let's say, is basically 3 cross 100. So what does 3 mean? 3 means 3 topics. So alpha is 3-dimensional. 3 cross 1. So alpha is a parameter for a Dirichlet distribution. So theta is 3 cross 1. Z is going to be, let's say the document has document has 500 words, so it's 500 cross 1, and W is going to be 500 cross 1. Okay, so document has 500 words. Okay, so what is 100? 100 is our vocab size has 100 words. And beta is essentially a matrix where each row corresponds to a topic. So there are 3 rows because of 3 topics, and so these are the parameters. Okay, we don't know them. I mean, so let's say we know them. Okay, we'll learn. So we'll address learning soon. So this is the distribution. So I wrote it as like a conditional, but it's not really conditional. These are random variables given parameters. Okay? So those are the parameters, and these are the random variables. Now you don't observe theta and z. Okay. Now, and we know exactly, because of the generative description, it's essentially equal to p of theta. First you generate theta, then you generate every topic, right? Product over I is equal to 1 to 500. Probability of zi given theta. So you generate one topic per word, and then given the topics, I is equal to 1 to again 500. You generate word itself given beta of zi. And in the sense it depends on zi. Specific topic, pick a word, right? So this would be the joint distribution. Okay. And each one has parameters. This depends on betas, this depends on theta. Theta itself, beta at least is a, so this we can just write it as parameters. Theta, okay, so theta depends on alpha. Let's put alpha here. Okay, given alpha. So this part was the Dirichlet distribution. This part was the sampling from multinomial, right? Or the categorical distribution. This part was sampling a word from again a categorical distribution, right? Any questions about just writing this? Because beyond this, if you don't understand this part, then we have to kind of stop here. This is fine for everybody? Yeah, so remember how for each document, how the words, how we are imagining the words appear, right? So the outer box, this represents the capital D document. So let's work it about the outer box for now. Okay. Each document appears as follows. First, you have some unknown parameter alpha. Based on an alpha, you are first creating a distribution, theta d. Okay. It's a distribution over topics. For example, theta d in this case was 3-dimensional because I said I had 3 topics: sports, books, and stock market. Okay. First, I generated theta, so that's why theta is a random variable. That's why it's appearing as the first argument in this probability distribution function. And then, given theta, I'm running a for loop n times, okay, the internal box, where I'm first figuring out what is the topic of each of my n words. That is zi, little d is fixed in its current document. So I'm figuring out the topic for each word. Okay. That's how I'm hypothesizing the document got generated. And so z's are saying for each word what is the topic it could have, and so z's are also hidden, in fact hidden random variables, and so I have a distribution, conditional distribution corresponding to them. Okay. So given theta, I can draw what the topic of each word is. Okay. And once I know that, given z's, then I can just say what potentially could be the word itself. The word is sampled from the topic distribution. So each topic actually is a vector, is a PMF. Okay. So 3 topics. Each topic is, let's say, beta 1, beta 2, and beta 3 is together form beta, and essentially PMF, with some probability masses, something like this, and this is going to be 3 cross, let's say 100, because my vocabulary has 100 words. So I draw each word out of my 500 words according to the topic that I chose for that word. Is that clear?
What is Z denoted?
Z is the topic of that word. First I'm hypothesizing what the topic of that word could be. Huh?
For the words in our document.
For each word in our document. Yeah.
So usually we have 3 topics.
Always you have 3 topics.
Yeah, for theta we have 3 topics. Then we go for Z, where we choose which one will be the
topic of each word, yeah.
Each word. And then we will figure out for a particular word.
Figure out the word, find what the word is by just sampling. Like, so this is a generative process. It's not, forget about the training data, documents that we have. This is how we are hypothesizing a document could have been generated. And first of all, you can see that there is no order relationship between words. It's just a bunch of words, yeah.
So topics are something I don't observe, right? So how
Yeah,
do
you
you
don't
figure
observe.
out which ones are topics?
What do you mean, which ones are topics? It's related to what he asked 2 weeks ago, but yeah, let's see. Yeah. So what is your question? Yeah. No, what's your question? Let's understand your question then.
So, given your input is only documents,
Yeah.
how do you learn that vector from topics?
How do I learn these betas?
Yeah.
I just specified, choose 3 topics. It could be 30 topics. I chose 3 here.
Number, okay, but
How do you get these numbers? These numbers pretty much describe what a topic is. Okay.
How do you get each topic?
What is meant by each topic? Each topic is essentially just this vector, right? Or do you disagree with that? What else is there to say about a topic than to just say this vector? Nothing else, right? So now you're asking how do I get these vectors and why do they even look different? Maybe that's your question. That's the second question. Let's wait for that. You have
No, I mean maybe the question is how we name those topics.
We don't name them. Nobody names them. We just look at them and
yeah, those words are in each cluster. In each clusters.
they look like that. Yes.
Yeah, and then afterwards we can name them.
Yes, we can.
They are weathers. They are
Sure. Sure.
So I think their question is like.
Why do I get different topics?
Yeah. So.
Yeah, we'll get there. Is that the question you also have? That's the second question. Any other questions before that? Like we'll get to that. Any other questions before that? No other questions? Okay. Why do we get different topics? Or it's not like we get names of topics. We get a bunch of distributions. You sort them. Maybe look at the top words with the highest weights, and they may look like they come from one topic or the other. As in like some of the one row will have, if you sort them, one row will have highest weights on maybe just sports related words. One row will have highest weights on stock market related words, and one row will have highest weights on books related words. Okay, why does it happen? Is the question. Okay, so that happens because we are trying to. So this is a joint distribution, right? If we had, so simpler case, if we had observed thetas and z's, okay, we don't observe them, although if we had observed thetas and z's, okay, then we can just do maximum likelihood estimation. Do you agree? In the sense, we have observed all the thetas, z's for a document, product over all documents. We have some joint distribution, and we're just trying to figure out what is the best alpha and betas which maximize this joint distribution. Okay, right? You can see that. So in this setting, you can see that to maximize the joint distribution, so let's say for a single document, you want these numbers to be high, right? Each of these, there are 500 terms here, 500 terms here, 1 term here, right? You want these numbers to be high, but to make these numbers high, what the method does is that it makes the topic vector sparse. In the sense, the topic vector has sum to 1, right? It's a bunch of weights that you're putting on, which add to 1. We are trying to figure out betas. Betas are essentially the weights. To maximize the likelihood, essentially, you're trying to maximize these weight numbers appearing in the document, but you can't maximize all of them because they are constrained. Okay. And it's happening across documents. So what these terms actually ensure is that, or kind of prefer, is that these betas are such that they are sparse, in the sense that there are only few words which have high weights and other words which have low weights. Okay, in each topic. That's what these terms do. And similarly, is the same intuition. And this term also tries to do the same thing. In each document, you want this number to be high. Ideally, you want all the 500 numbers to be high. Okay. So for each document, also it will try to produce a sparse number of topics. Like all the put high weights on few topics and low weights on the other topics. Okay. In the sense, a single theta that you produce, that theta will have, if there are 3 topics, one of the theta will have high weight and other thetas will have low weight. But let's not worry about this. Here your question was, why do the betas look like they are clusters of same type of words? Okay. When I said this, that they have to be sparse, as in they try to put high weights on some of the words and low weights on some of the other words. Turns out that it puts high weights on co-occurring words. If the words are in the same document, because for each document I need to maximize the likelihood essentially. It's a product of them. So I kind of put high weights on words which are in the same document, which are essentially which I'm saying is they're co-occurring. Okay, and that's why we get essentially topics with we'll have a beta with some very high weights on one. Let's say if the document was actually about sports, then the sports words have high weights for this document. Okay, and the other weights would be 0 because that would be the optimal configuration to maximize this likelihood. Is that clear? That's the intuition behind it. I mean, of course, in terms of computation, it's just a mechanical thing. But do you understand what's happening? We just want to maximize likelihood, and that's what's giving, because the constraint it's giving you, each topic is essentially capturing co-occurring words, and it being sparse is essentially like cluster of similar words. Similar words just means they are occurring in the same document. Okay. For a different document, maybe some other words you want to put high weights so as to maximize likelihood. Then those words will be in a different document, because you can't put weights on the first set of words and the second set of words because you have a limited budget, which is they have to sum up to 1. Okay.
So the beta vector is learned from training set of document.
Yeah. So given this, we have to maximize the likelihood, right? I mean, that's how we learn alpha and beta. Yeah. I mean, learning is all. Today's lecture is about learning, and learning is all about what happened there. Okay. Yeah, learning is all about learning the beta and the alpha. Okay. Right. If you knew beta and alpha, you can do inference. That would be given the new document. Okay. You want to find the probability that probability of maybe theta given just the words. You can find that. You do summation, conditional expectation, things like that. You can find that. Right. So probability of finding a new document would be what is the probability of theta given word vector. So this is going to be probability of theta comma word divided by probability of word, right? And each of the terms is essentially a integration over something else, which is z's of p of theta comma word, integration over z or whatever summation, and this is integration or summation over theta of p of theta comma word comma or theta comma z comma word, right? So given this object, if you knew this object, which is essentially means you know alpha and beta, then you can find what is the probability of theta given the words, which is essentially the document. Given the document, I can tell you what is the weights of this hidden variable, which happens to be a distribution, and therefore I can tell you what the most likely topics are for this distribution. Right? I mean, that's just a function of joint distribution. If you knew the joint distribution, you can compute these things. Right? What's the time? When did we start? 6? Okay, so we're gonna take a 5-minute break. Okay, so we'll resume actually. So again, I'm skipping conditional random fields because they are not very difficult to understand. Most of the complication arises with directed graphs. Undirected graphs is really, it's just factors and you maximize the likelihood of the factors. So, so conditional random fields, anyway, the first few applications I really did not talk about how do you learn the parameters yet. So actually the learning part is going to start soon. And just coming back to LDA model, I said we need to learn alpha and beta. How do you learn alpha and beta? Maximize likelihood is what I said. But I said that would be the case if I observed the hidden random variables theta and z. But if you don't observe theta and z, how do you find alpha and beta using just the data, which is just going to be documents, right? The W's or the document words. For LDA specifically, there is a method called variational EM. Okay. Why is there a method like that? The high level idea, which I will not go into variational EM at all, is that EM is all about, if you remember, I had kind of gave a high level intuition of what EM does in the expectation step. You want to find in the E step, you want to find the probability of theta and z. Theta is also vector, but theta and z given some parameter, candidate parameters w, alpha at time step t and beta at time step t. Okay. So EM algorithm kind of does something iteratively. So at time step t, you have parameters. Let's say you need to find this. Okay. So this part is a bit complicated, computing this. So what the variational EM just says that you kind of don't compute this, but compute something else, some other distribution Q. Okay, now you guys can't see probably. Instead of this, compute some other function Q on theta and z, which depends on some other parameters. Okay, some parameter gamma of w, and let's say some other parameter p of w. So what I'm saying is, LDA is also learned using EM style algorithm, except that in EM, as I said, whatever you don't observe, you have to have an estimate, some probabilistic estimate of what those values could be. In LDA model, it turns out because of this type of a description of the joint distribution, this conditional distribution is like a messy conditional distribution. So there's one additional step included in LDA model, which is to approximate this conditional probability using another conditional probability. Okay, that's the variational approximation part, and then just do EM. M is just use Q and maximize likelihood. Okay, which will be something like this, but without the alpha and betas. Now it's going to be gammas and p's. Is that clear? I mean, so it's just EM, except there's an intermediate variation step, in the sense I'm approximating a distribution with some other distribution. If you remember variational autoencoders, there was a one conditional distribution of, I think, z given x, which is being approximated using a neural network. Right? So similarly here, the probability of something given, some hidden variable given observed, is being approximated using some joint distribution. I'm not going to write it, but it's some easy to work with joint distribution. This conditional distribution, if you just directly compute using this product form, is a bit messy. That's why there's a slight variation. But don't worry about this. I mean, so that's this is just to say that we're not going to look at variational EM, because we want to kind of understand just EM first, and so we're going to look at EM now. Okay. So let's see. Okay, so there are many types of learning problems here with this joint distribution learning, right? Parameters of joint distribution learning. There is directed graphs, there is undirected graphs. You may have complete data, you may have incomplete data, which means that things like this, where hidden variables are there. So you don't see in hidden Markov models, Gaussian mixture models, LDA, you don't observe how some of the variables are hidden. So which means they are incomplete data. And structure of the graph may be known, as in you know conditional independence properties. Maybe you don't even know the conditional independence properties. Okay, you just have a bunch of 100 random variables. You don't know anything about how they are related to each other. Then you may first want to just learn the structure of the graph, which means what conditional independent properties may be true for this set of random variables. And you may have things like whether you want to have generative. You care about. So if you care only about prediction, then you can kind of do a shortcut. Maybe some of those random variables are output random variables and some of the random variables are input random variables. Then you may only care about some estimating the conditional distributions rather than this distribution, original distribution. So those are all variations of learning problems. Is that clear? I mean, so this is just a way to break things apart per type of issue. That's all. So first we'll look at, so here I've listed so many, 5. But first one will be just maximum likelihood estimation. Essentially, I'm going to look at 5 different learning problems, although there are many others. If you see the previous slide, you can match and mix and you'll have too many learning problems. Here I'll look at maximum likelihood estimation. Actually, I'll try to skip most of it because it's kind of straightforward. MLE is something that many of you must have seen. Try to spend a little bit more time on EM. Okay, EM in this context, for especially people who have not done 575, we'll kind of spend more time here. And then learning structure and these, if we have time, we'll cover this, otherwise skip this. that's the agenda for the rest of the 1 hour. Half an hour or 50 minutes. Okay, so let's pick directed graphs. So let's pick the first case. Directed graphs, I have full data. I know the structure of the graph. I just want to learn a parameter. That's it. That's the problem. Right? So is the problem setting clear? I'm in the directed graph model setting. In the sense, I know I have a joint distribution. I know its graph. I know its graph, and I have all the data corresponding to all the random variables that are present in that joint distribution. Okay? So there's nothing hidden here. So given this, can you tell me what the parameters of the joint distribution are? Right? So this doesn't work. So if not anything, this is a key slide for learning. Okay. If a graph is like this, direct probabilistic graphical model, and A has two parents, B and E. Okay. Then there will be three factors. Okay. There will be a probability of B, probability of E, times probability of A given B comma E. Right. So by parameters or learning, all I mean is you want to fill in these question marks. Okay. You want to find the probability of B equal to 1, probability of B equal to 0. They have to sum up to 1, so essentially there is one number here. Here also there is one number that you need to figure out, and here you have these many numbers to figure out, assuming all these are binary random variables. Okay. Is this clear? So by parameters I just mean in this setting these question marks. How do you fill these question marks? Is this clear? Who's not able to kind of not sure what this is what by definition I'm saying these are the parameters I need to learn. If I know this completely specifies the joint distribution. If I know these numbers, right? If I know all these numbers, it completely specifies the joint distribution, then I can do all sorts of computation, like things that I wrote here, right? Probability of A given B comma, probability of D given A comma C. That you can't really read out directly here. So B given A comma E, you have to do something like this, use base rule, use a total joint distribution, and use those numbers from the table. Do you want me to illustrate that, or it's fine, right? Because we have to cover something interesting. So the name of game here, this is a simplest setting, but we'll just given a bunch of data. This is the assignment of those random variables, A comma B comma E or something. Just find these local conditional probability values, those question marks. Okay. And so a simple setting is this, right? So let's say there's only one random variable R. There's no edge, there's no other random variable, and it takes 5 values. Okay. Which means that the parameters are 5 numbers. In fact, 4 numbers, but parameters are 5 numbers. They have to sum up to 1. Sum of these numbers, P of I is equal to 1, right? So those are the 5 parameters. And let's say I have this training data. Okay, these are the observations that I've made. 1, 3. I mean, I've just sorted it. These are the observations I've made. From this, you can very easily eyeball what these numbers should be. Okay. What do you think? So given this data, the parameter for this one random variable, this one random variable takes 5 values. You just need to figure out the PMF. What is PMF values are? So what do you think P of 2 is? Yeah, P of 2 is 0 because 2 did not appear in the data. What do you think P of 1 is? 1 by the length of this, maybe 10 numbers here. Yeah, 10 numbers, so 1 by 10, 0.1. So that's it. That's count and normalize. Okay, count the proportion of occurrences divided by number of observations. Okay, this is not needed. Yeah, I mean the other 2 examples that I skipped in between are essentially the same thing, count and normalize. Okay, so let's not worry about that. So next interesting case, the previous ones are the same as the first example that I showed. Next interesting case, let's say there is a hidden random variable G which takes 2 values, and there are 2 other random variables which take 5 values each. Okay, in this case, there are ratings and genre, and then maybe ratings depend on genre and these guys. how they rate given the genre. And maybe the graph is like this. So given genre, there's some realization of this guy, there's some realization of this guy. Probabilistic. This is all probabilistic model. There is no deterministic relation between being comedy and high rating or low rating or something. Okay. And so the genre distribution for these three random variables, let's say looking at the graph, we know that it's P of G, one term for this guy, one conditional term for R rating given G, another term for rating 2 given G, right? Now, from this, actually here, I mean, let's say there's a bunch of training data. In this case, there's a rating and what are the ratings of the two guys and what is the genre, okay? Maybe this is not observed, we'll get to that, but let's say this is your training data. It's not difficult to actually, again, compute parameters of this guy, and this guy. So what are the parameters of P of G? It's going to be what is the proportion of B's in your data, what is the proportion of C's in your data. C's is 2 by 5, and D's is 3 by 5. Okay, that's it. So P of G is easy to compute. Is that clear? So P of G, the parameters will be 2, whether G is equal to D or C, right? And P of G would be 2 by 5, I guess. No. 3 by 5 and 2 by 5. Okay, that's how you infer this from the data, and similarly you can infer this guy and this guy. Okay, for every G value, whether there was a corresponding rating 1, 2, 3, and 5, you just count the proportions, and whatever proportions they happen to be, you just use them. Okay. Now, the key interesting or the key change from this example to the previous example is that I can do what is called parameter sharing, and and this is similar to what I kind of alluded to in the hidden Markov model setting, which is that I'm going to say that P of G is fine, just be computed. P of R1 and P of R2, I'm going to say these two are the same conditional probabilities. Although they're two different reviewers, or in this case, I'm going to say they'll have the same conditional probability, which means that I can aggregate data. Right? There's no separate identity for R1 and separate identity for R2 anymore. Okay. So I can use data. So for a genre, I can actually assume that 5 and 3 are two different observations of the same random variable, let's say R, one random variable R. So all I'm saying is, if you have this data, just make each one 2 with just one number next to it. Okay. So that's parameter sharing. Although originally there were two different people, I'm just kind of removing this and saying there's only one random variable R and you have more data. So all I'm saying is I can compute one P of R of rating given genre. That's it. That's parameter sharing. It's the same, although here there were different random variables R1 and G, R2 and G. I'm saying there's one random variable R and one random variable G. So it's like parameter sharing, because in hidden Markov model setting, I said h t plus 1 given ht is the same as ht given ht minus 1, and so on. So these random variable indices don't matter. It's just how do I go from one random variable to another fixed random variable. So there was a p transition. There's a single conditional probability. Instead of one conditional probability per index of random variables, there was one single conditional probability. Yes, that's what I'm saying. Okay, so that's one simple observation. Is that clear? Okay. And that's what I've drawn. I mean, this is clearly computed by this eyeballing. This part I'm saying just make 2 copies per observation, and then think of, instead of 2 conditional probabilities, I just have conditional probability of rating given genre, and then I can compute by I mean, this is just normalization, but yeah, for every value of rating and genre, I have to compute this. I mean, there's a condition on genre, right? So for every value of C, 1, 2, 3, 4, 5, D, 1, 2, 3, 4, 5. If I've never observed D and rating 1, then it's 0. Out of this, I have 6 observations here with D, and 4 observations. Oh, wait, what is that? Oh no, I mean in the data I have, you'll see that I have 4 observations. Well, in the data you can see how many observations I have, but this is just the counting of with C how many times did C 3 co-occur, how many times did 2 co-occur. With C 2 co-occurred 1 out of 4 times, that's why it's 1 by 4. And for example, with D 4 co-occurred 4 times, so sorry, 3 times out of 6, so it's 3 by 6. I mean, so we can actually just look at here, right? So we can see that with C, 1 co-occurred once, 2 co-occurred once, 4 co-occurred once, and 5 co-occurred once. 3 never co-occurred, right? So in the next slide, we say since 1 co-occurred once out of 4 times, 1 by 4, 2 co-occurred 1 out of 4 times, 1 by 4, 3 never co-occurred, 0 by 4, 4 co-occurred once, 1 by 4, 5 co-occurred once. Is this co-occurrence frequencies? Okay, so that's it. That's what directed probabilistic graphical models, known structure, all the variables seen. That's what it is. Okay. Let's skip this part. Counting and normalizing is fine. So when data is complete, it's kind of an easy problem for directed graphs. In fact, you don't even have to think of maximum likelihood estimation. The maximum likelihood estimation just turns out to be count frequencies of things occurring in the data. Okay. So at least for discrete random variables that we saw. Now the interesting part is when there is incomplete data. Okay. In the sense when there are hidden random variables. In HMMs there were hidden random variables. LDA there are hidden random variables. In GMMs there are hidden random variables, right? So how do we estimate that? That comes to the point of EM. Okay. So what if we don't observe G? We observe ratings, or we don't observe G. But we hypothesize that there is a G, and there is a relationship from G to R this way. The two R's this way. Which means I've hidden all these D and C that you observe. Okay, drama versus comedy. I removed it. Okay, and I still want to estimate P of G and P of R given G, for example. Those are the two things, right? How do I estimate them? So in terms of notation, I'll say my hidden variable is G because I don't observe it, and my observed variable or evidence is going to be R1 and R2 because I observe ratings. In terms of just the notation I used in HMM slide, and for example, R1 and R2 will be 4,5 for example, and parameters are still P of G and P of R, right? Those conditional probabilities that I said. And so what, I mean, we only observe R's, so we should be just maximizing the observed data likelihood. We want to maximize the probability of observing data given parameters. Okay. So we want to just maximize, this is observed data only, probability or E. E is the only thing that we observe, ratings. Okay. What is theta? Theta is still P of G comma P of R. Those two, the two numbers on this side, and maybe I don't know how many numbers, but a lot of numbers, 2 cross 5 numbers actually. So let's say this is 10 cross 1 vector P of G, right? For every for every genre value, or for every rating, you had a number, right? So that's theta. I'm just maximizing the likelihood of the observed random variables, okay? Because that's the only thing I observe. But okay, so I want to do this. So I hypothesize that there was this hidden random variable G. Right? I mean, in this case, I've been told that this is the graph. G I don't observe. So I don't know this. This is actually the marginal distribution of the observed from the joint. The joint is going to be, for us always the base, object is the joint distribution of random variables. So I have to sum over the things that I don't observe, which is these hidden random variables. In this case, just G. Right? I mean, from here to here, this is equal to this by definition. This part is equal to this part. And maximum likelihood is just saying maximize over the product of the data. Every observation you see in your data, every tuple, there will be a product here because implicitly we are assuming IID type of a setting. Okay. There's no temporal relationship between one tuple of observation and the other tuple of observation. So that's the same this part. So this is just likelihood maximization problem where I want to maximize over theta. Theta is just these numbers. 2 numbers here, 10 numbers here. Or 1 number here, 9 numbers here. It's the same. Okay?
This means the general distribution of H, E of H and E is equal to E of E.
Where does it say that? There's a summation here. This summation, this whole thing is equal to T of E by definition. That's true. Right? Like in this case, H is G, and G can take 2 values. So there's 2 terms here. The sum of these 2 terms, there's one term for H is equal to drama, there's another term for H is equal to comedy, and the sum of 2 terms is actually just equal to this. Right? Okay. And to do so, we'll do something related to k-means. Okay, so if people don't know k-means, let's not worry about it for now. So again, EM template. What we're going to do, because it did not observe hidden variable g, we're going to try to compute the probability that g could have taken some value, drama or comedy. Okay, probability that g could take a value drama or comedy given each observation. I'm gonna for each observation, I'm gonna say what would have been the probability that it was based on the hidden one was actually a drama, took the realization drama. What was the probability that the hidden one actually took the value comedy? Right? There will be 2 numbers, for example. And how do you compute this? Use an inference algorithm. This is a conditional probability. Okay. But for that you need a theta. So you start with some candidate theta. Some candidate, you fill those tables, the 2 numbers and the 10 numbers. Start with some 2 numbers, 10 numbers. You can always compute this conditional probability. So it's just computation, right? Because I know the joint distribution if I know the 2 plus 10 numbers. I compute this. For each evidence I can compute this. Okay. Then what I'm going to do is because I have these numbers, right? One per observation, one number or 2 numbers per observation. Because per observation, let's say there was a observation. So rating 1 was rating 1, rating 2. It was let's say 4,5. The hidden guy, which is actually equal to G. I don't know why we're using 2 different notations, but let's say hidden one was drama. Okay. What is the probability of this? Maybe it was 0.6. I mean, so maybe by doing this conditional expectation, I got some probably 0.6. For the same observation, it being comedy was the opposite. They have to sum to 1. Okay. So these probabilities that I computed, I'm going to call them weights. Okay. And I'm going to now, in the M step, imagine that I have 4,5, D, but it has a weight of 0.6. I'm going to imagine that 4,5, D, this C, so there's not going to be a question mark anymore. I'm going to assume that they have to have 2 observations, 2 sets of observations, one with a D, one with a C, but each observation will have a weight of how important it is, which is 0.6 for the first one and 0.4 for the second one. And these numbers are nothing but Q of, this conditional probability of H is equal to H given that observation. Okay. That I can get given theta and my joint distribution, I can compute this conditional probability. Right? And that's it. Once I have this weights, I have full data just to maximize the estimation. If I have full data, doing maximum estimation is easy. That was the first setting. We are in the second setting now, thinking of EM. Okay. And I don't know if I have an analogy to k-means. Yeah. So one kind of way to understand EM is through k-means clustering. Okay. So why did I suddenly bring up clustering into this picture? So don't worry about the running examples for now. Just think of what is k-means actually doing. Okay. K-means objective is to estimate clusters, right? You have a bunch of points. Those are the only things observed. I want to find 3 clusters. Okay. Let's say k is 3 here. We don't know which points belong to which cluster. So we again do some sort of a optimization approach. First we say, okay, let me hypothesize that each point belongs to some cluster, one of the, let's say 3 clusters, one of the 3 clusters with some weight. Okay, and in fact the weights are going to be such that each point in the E step only belongs to one cluster. So in the EM algorithm, since I did not know the rating, drama or comedy, I would say with 0.6 probability maybe it was drama, with 0.4 probability it was maybe comedy. If I have 3 clusters, I don't know which cluster it is, I'll pick each point to be exactly in one cluster. So instead of saying 0.6 in first cluster, 0.2 in second cluster, 0.2 in third cluster, I'll say 0.1 in the first cluster. So that's what it does, K-means does in one step, okay, like the E step of EM algorithm. And then once I have assigned the points to the clusters, in the M step, I'll find new cluster centers. Okay. So that's cluster centers are essentially the parameters in the K-means clustering algorithm. So assuming some cluster centers, I'll assign points to clusters, but in a very extreme case where there is no distribution but just one point as a cluster, corresponding cluster. And then given those assignments, I'll find new cluster centers. That's the M step in K-means. Okay. So EM is like a more generalization of that. I mean, this is the analogy. They are working on the same type of principle. Yeah, let's just look at an example actually. I mean, same example, but now, somewhere I did 4,5, but let's not worry about it. Let's say this is the example. Okay, I have exactly 2 data points. I don't know the genres, but I know rating given by the first guy, rating given by the second guy, rating given by the first guy, rating given by the second guy. I don't know what these are, but I want to learn. I don't want to just figure out what question marks are. Figuring out the question marks is an inference problem. The learning problem is to even learn what is P of G and what is P of R. Right? In this case, since only let's say the ratings can only take two values, 1 or 2. Okay. In the previous example, it was 1 to 5, but in this case, let's say it's 1 or 2. So that means I need 2 numbers for P of G and 4 numbers for P of R. Right? Every combination, essentially. Right? C with 1, C with 2, D with 1, D with 2. Okay. So these are the parameters I need to. So basically, think of, I don't know these 4 numbers, I don't know these 2 numbers. Those are the ones I ultimately want to figure out. Okay, that's the learning problem. Okay. Now I'll start with some set of numbers. Okay, some arbitrarily chosen numbers. In the E step, I'll try to find the probability, which is the Q function, probability of the hidden variable given the observation 2, 2. Okay. So what are these first row correspond to? First row is saying, so first row and second row are saying observation is 2, 2. What is the probability that G took the value comedy, or what is the probability that G took the value drama? Okay. How do I find that out? I first compute, because I know the parameters, I can compute the joint distribution. Joint distribution is nothing but, we know that in this graph, the joint distribution is probability of G, which is 0.5, times probability of R1 given G, probability of R1, which is 2, given G, which is C, is 0.6, and R2, which is also 2, given G, which is C, is 0.6. So I just computed the total probability, but so this is kind of not needed, but I'm just saying, given the parameters, you can always compute the joint distribution. Given the joint distribution, it's easy to compute the conditional distribution, and turns out to be these numbers, okay, 0.69, 0.31, 0.5, 0.5.
And here the P of G and P of R in G is initialized with something.
I just arbitrarily initialized here. Okay. Now I've gotten these. These are going to be my weights. Okay, 1, 2, 3, 4. This is going to be my weights. As if I'm saying this is going to be C, 2, 2 with weight 0.69. It's going to be D, 2, 2 with weight 0.31. It's going to be C, 1, 2 with probability with weight 0.5, and it's going to be D, 1, 2 with weight 0.5. Okay, and then in the M step, I just do counting and normalizing. We did this exercise in the first example, but counting, when I'm counting, instead of counting once, I'm going to count these weights. Okay, when I was counting number of times C appeared, I'm going to look at weights only, not, for example, if I think of this as my data set, how many times does C appear? 2 out of 4 times. Right? I would say 2 by 4, but that's not what I'm going to do. I'm going to look at these numbers and say C appeared in the first and the third row, So I'm going to add these two divided by all the numbers. Okay, so that's what this is. 0.69 plus 0.5 divided by all the numbers happens to be 0.59. Okay, it's just weighted averaging rather than counting. See up here, two instead of 2 by 4, I'm saying look at the weights, add the weights, and then divide by total number of observations, divided by the total weights. It's like weighted averaging. And I do the same for D. Okay, so that's now a new parameter, P of G. So now this got replaced with somebody else, which is this P of G. Similarly, you can find P of R again by counting and normalizing. Okay, this is not difficult, but you have to spend time on this. So you get new numbers. Now these 4 numbers and these 2 numbers are new guys. Again, you compute joint distribution, the Q, and keep repeating this. So of course, you will not do this by hand. You will run a for loop and do the EM algorithm in reality.
How do you count to the second one?
Where this one?
The next one.
This one.
Yeah. So
Yeah, how many times will C and 1 co-occur? No, given C, how many times does, so given C, where is C? In the first and the third one. How many times did 1 occur? Once. Right? So if it occurred once, then you use 0.5 as a weight instead of once. Okay. So let's say with C, how many times do 2 co-occur? These two occur 3 times. Right? But I'm going to, instead of writing 3, I'm going to use 0.5 and 2 times 0.61. That's what I do. This is just a way to run EM. And now coming back to your question about, you had a question about what is initialization with things left off or something. You had a question, I believe. You don't remember now? So what if you had one more observation with multiple question marks? Okay, not even that.
Realization is
Yeah, some realization is missing, right? Okay, so how did I get to these numbers? Let's try to answer that, because here I said I just arbitrarily initialized that. Does it look like that? Yeah, okay, here I think it's arbitrary. So let me come back to that question again. So how much time do we have? 8 up 3. Okay. So okay, what I'm, the initial remark that I made, and it's not in this example, is that if you haven't, how do you get these numbers? The way you can get these numbers is by ignoring. So let me actually draw something on the board. So let's say you had observations, and what was it? 2,2. 1,2, and maybe it is 2,1, 1,1, and so on. And let's say there are many observations like that, and I don't know these question marks anyway, right? I don't know these anyway. Let's say I don't know any of them, and maybe I have a missing entry here. I don't know what this is, and maybe I know this is 1. Because it's not expected that both people will rate everything. And maybe I have maybe 2 here, and I don't know what this is. Maybe let me put a box. Okay. And all I said was the way let's say this was your data. Ultimately, you want to know parameters, learn P of G and P of R. All I'm saying is the initial P of G and P of R you can get by ignoring this data. You can ignore this, and you can get P of R. So because I haven't observed any P of G, I can say this is all 0.5 uniform probability of being either this side or that side. I can reasonably make a case for that. Or if I have prior, then you can use those numbers. There I think is 0.5, 0.5. And these guys, since I don't know these numbers, I can delete those observations and then just use these numbers for estimating P of R. Okay. That's all I mean by ignoring things which with which I can't do. So initially I'm not doing EM, right? I somehow need to fill these numbers, and a reasonable way to fill these numbers is to just use essentially something like fill reasonable numbers for if a whole column is missing, or if observations are missing, just delete them. That's roughly that. Any other question? Okay, so let's go to the third setting, which is directed probability graphical models, but now I don't know the structure. Okay. if I don't know the structure, I think the first order of business is to learn the structure first. Forget about the parameters. Okay, because if I have this diacritic graphical model and I have data, of course, maybe it's incomplete or complete, whatever. But I don't even know the structure. First, let me learn the structure. And if I know the structure, then I'll mean this side. Then DPGM, structure known, maybe complete or incomplete. That's 2 settings that we studied. Okay. So learning the structure is the first order thing. So let's not worry about learning the parameters. And for learning the structure, there's really no silver bullet. You just have to do some sort of a base rule type of thing. So what is learning the structure? If you have, let's say, 2 random variables, then you have these are the 2 structures. Either they are independent, there is no edge between them, or there is an edge between them in this way, or there is an edge between them in the other way, right? Right. And if you have 10 random variables, then you have all sorts of graphs which are possible on those 10 random variables, right? There are many possibilities there, right? What you'll just do is essentially you have to somehow figure out the probability of a particular graph given data. So I'm not going to go into the details of this section, but I'm telling you how would you learn a structure. You would want to score for every structure a number, right? Probability of the data, given data, what is the probability that this would be the structure, which is like what is the likelihood of this structure given the data, what is the likelihood of another structure as in the graph given the data, and of course they have to sum up to 1. And if you know this, then you can maybe pick this structure because this graph seems to be more likely than the other one. Now the question is, how do I get this? That is something I've not mentioned here. How do you score a graph given a model? Okay, so given a bunch of data points, right? Given a bunch of realizations of the XY random variables. That actually is not a satisfactory, in the sense people have not figured it out satisfactorily for in general. For tree-based, if you assume these graphs are, for 2 random variables it's kind of easy, but let's say for 10 random variables, if there was only graph type of relationship between them, tree type of relationship between them, there is some algorithm called Chow-Ju algorithm which from 60s or 70s which can solve it. But in general, it's not clear how to get a structure. What is the probability of a structure given a graph? So learning structure is a hard problem because it's combinatorial, right? You have so many choices, so it's difficult. I don't have more to say about this. This is just base rule, so that's not worry about that. Okay, so the next 2 slides were just giving some comments. Ultimately the problem is hard, as I told you, it's combinatorial in nature. And if you could score structure given the data, then you can do some sort of base rule, average out the choice of structure and so on. So that's what those 2 slides were covering. Let's come back to the last couple of parts. Let's look at undirected probabilistic graphical models. If you remember, I think none of the examples that I gave so far were undirected, except for conditional random fields, which I kind of skipped. But I also told you that undirected graphical models are used for images. So there is some intersection between deep learning and undirected graphs. So one prominent example is image segmentation. It just means that if you have an image, you have to segment, as in, let's say you have a landscape image, then you have to say that all these pixels correspond to the sky, all these pixels correspond to land, and maybe there's an object, all these pixels correspond to that object. Okay, that's image segmentation. So you have to assign a label for every pixel, essentially. Okay, so that's a really hard classification problem. You're just saying whether this pixel does it belong to land, does it belong to the object, or does it belong to sky? Okay, it's a 3-class classification problem. The way graphical model or undirected probabilistic graphical model comes in is that you're going to say each pixel is a random variable. Okay, it is related. Its label is related to labels that nearby pixels will also take. Okay, that's how you will draw an undirected edge between a pixel and its neighboring pixels. Okay, that's why you'll have a planar type of a graph where each pixel is related to pixels next to it. adjacent to it. Okay, and then you're just figuring out the most likelihood assignment of these random variables given evidence, like given the pixel values or whatever, what labels it is. K-means clustering. You can use K-means. So no, image segmentation. I'm just telling you how to do it with undirected graphs. K-means clustering is something that you can also use maybe for image segmentation. Maybe it works, maybe it doesn't. But here I'm just telling you how to use graphical models for image segmentation. Okay. So let's look at this directed graph, a simple example. So this undirected graph, we don't know directionality. Okay? There's this random variable, this random variable, this random variable, and this random variable. And if you remember, potential functions are just factors. Okay, factors. So this joint distribution of these 4-dimensional random variables is going to be just the product of factors. Okay, and these factors are going to be cliques. If you remember, either I could have written a joint distribution with factors or terms which involve these two, these two, these two, and these two, because each one is a clique. Or I could write a product of two terms where one term is smoking and cancer and the other term is cancer as one cough, because this is a clique. Okay? So those are the only ones I'm allowing by definition. Okay? And for example, here for this clique there's a factor. Okay. So factor just is basically taking two arguments. What is the value that smoking random variable takes? What is the value that cancer random variable takes? And some scoring for that. Okay. And these are factors precisely because they don't have a sum up to 1. Okay. In the directed graphical model case, you first of all you would have a random variable given its parents, and of course because of that random variable has a sum up to 1. I mean the probability of this random variable taking several different values has a sum to 1. Right. But here is just a notion of factors. So the arguments of a factor are just some subsets of random variables, in particular those which form cliques. Okay, just to recap what UPGM was. Okay. So instead of So instead of thinking of this product of factors, right? What we're going to do is, since a product of terms, right? It's like term 1 times term 2 times term 3. Let me actually write it as a term 2. I'm going to write it as equivalently as e to the power sum of terms. Okay, so which basically e to the power term 1 plus term 2. Okay, this is valid. Oh, sorry, log. Oh my god, now it can't read it. Okay, plus log term 2. Okay, so that's what I kind of say, that let's think of this as e to the power sum of, instead of log of terms, I'm actually just calling them as weight times some other terms. It's just a renaming of, because I don't have the excluding of log. Because first of all, I did not know what the factor was, 5. So I can think of w times so log of 5 as w times a 5. That's as simple as that. And the interpretation for that is you can think of these f's to be feature functions, or the functions of a subset of random variables, and wi as a weight of that feature. Okay. You don't really have to kind of make this distinction, but you can just interpret it that way. Okay. So, for example, this feature can be, first feature can be smoking and cancer is 1 if something happens, 0 otherwise. That can be right. Any questions about this transformation? All I've done is there's a product of potentials or product of factors. I just said e to the power sum of some other things, and we know that these are functions of random variables, so I can always make functions like this. which are depending on what values you take. If smoking is false or cancer is true, then it's 1 or something in this case. Okay. So if I make functions like this, what I'm heading to is that we can learn W's. That could be one learning problem. Okay. Okay. Where is the okay? So if you take z's are anyway normalizing constant, so it's going to depend on w's, but okay, so it's going to depend on w's. So let's take the log of p of x, because ultimately, x is a random variables. Let's say we observe all these random variables. Then we're just trying to maximize the log likelihood. It's all about maximizing the log likelihood. So take the log of this. Then you'll have some terms like this, minus z of parameters like w's. Okay. And that is what, if you take that and then take a derivative of that, derivative of the log likelihood. I've not shown log likelihood explicitly, but you can see in the previous step I had, so let me just write the log likelihood. Log of p of x would be just wi sum over I, wi fi of x minus z of I guess w's. Okay, right? Oh, sorry, there is a log. Okay. Now it turns out that the first derivative of this guy, log likelihood, happens to be so actually you can substitute data here. So let's say f self x, you can substitute data here, right? Log likelihood of a specific data point xi, xi 1 to n. Then you'll see that the first term is essentially corresponds to some sort of number of times feature I is true in data. So in the previous case, in the example, I had a feature which was just on or off. It was either 1 or 0, right? Fi was 1 or 0. All I'm saying is that if you take the derivative with respect to the ith weight, which was corresponding to the feature I, it's just going to count the. If you take the derivative, this term is going to go away, right? It's just a function of. Take the derivative of. With respect to wi, only this term remains, right? All the other wi's vanish, and this term is just an indicator type of feature. So it's just going to count the number of times the feature was present. Okay. Right? Why are we taking the derivative? Okay, so even before this, we want to just find the parameters of this guy, and the parameters of this guy are w's. Okay. And to get the parameters, since we have the log likelihood as a function of parameters, we can take the derivative with respect to the parameters we care about, make gradient step, and update the parameters. So we are just doing some sort of a gradient update method for finding the best parameters for my data. Second term is a little bit more complicated. Why taking the derivative of the log of z of w will give you expectation with respect to w of something. Just take it as a fact that this is true. And but since there is an expectation with respect to w, you will have to do something more. I think. So because there is an expectation here, you have to do inference. Remember, for a given value of w, for the given current value of w, you have to do inference to find these expectations. Once you find this expectation, you can substitute that number here. You can this is just based on data. You can compute this number here. The sum of these two, or the subtraction of these two, will give you the gradient with respect to wi. Repeat that for every w's. You'll get a big gradient vector. Subtract it with existing w's, and then you'll get a new w. So it's gradient descent, but I just wanted to kind of show that it's all about manipulating the log likelihood of data. Okay? Even for undirected graphs. Just think of the context. It's undirected graphs. We just have to manipulate, figure out the parameters, and by making the log transformation, the parameters just happen to be the coefficients of some deterministic functions. Okay? That's it. Any questions at this point? I think everybody's tired. Okay. Okay, let's not talk about this. Yeah, there's some shortcut for previous thing. Okay. So undirected probabilistic graphical models, we saw generative model. Generative just means there was no notion of input and output variables. Okay. Now discriminative just means there's going to be some distinction between input and output variables. Okay. Some random variables are going to be input, some random variables are going to be output. So the update equation is going to be very similar. You know, it's just going to be maximizing the log of the likelihood, a different likelihood. It's the likelihood of output variable given input variable. Okay. So in the sense conditional likelihood, that's what it is. It's conditional probability. And so just going to be again counts, which involve both types of variables, taking some values. So count, you're going to again define some features which involve input and output variables. And so these are counts of how many times that feature was on. Okay, that's going to, the weight of that will be updated according to this gradient. And again a similar expectation. Okay, so nothing much changes except this likelihood term changes to conditional probability of y given x. Okay, because that's what you care about in a discriminative setting. In discriminative setting, your main object of interest is not the probability of all the variables itself. In discriminative setting, remember this was a question in the exam as well. You care about the conditional probability of output given input. You approximate those using linear functions, for example, in Gaussian integration and things like that, right? So here we care about the conditional probability distribution. Same thing. Wow, there's incomplete data as well. Okay, we'll skip this for now because so it's UPGM, discriminative, and incomplete data, which is even more complicated. So let's skip that. Yeah. Okay, so in summary, we looked at the following problems. MLE, which is counter normalized for directed graphs, it's kind of easy. So if you did not know there was a directed graph, you just explicitly do maximum likelihood estimation. Okay, explicitly have a parametric form for your joint distribution and maximize the parameter of that. And how do you do that? You can do by gradient descent. You can find the gradient of the likelihood with respect to your parameter, update your parameter by adding to your previous parameter a scale version of the gradient. Okay. We saw EM. Okay, this is all about I have some hidden random variables or missing random variables. I can kind of estimate what those random variables could have taken value given my current parameter estimate, and then given this estimated. Now that I've completed the data, I can look at the completed data and then just do maximum estimation. That's what it is. So you complete the data in each step, and in M step you maximize and get new parameters in the M step. Okay, and we looked at some variations like structure. We didn't discuss much, and we just discussed generative setting. We discussed generative and discriminative setting, yeah, but not incomplete data. Okay, so one last thing I want to, two things. Okay. Yeah, as I said, the learning problem generally becomes harder and harder the more complicated your graph is, and if you are missing data and so on. Yeah, and just to kind of before I kind of close this stuff on graphical models, I said there's missing data here. Remember, so in this example, for example, you had missing data here, right? So I said there's a box here, maybe you didn't make measurements of these reviews. Then you kind of ignore this and start with your PR and PG, right? But you can also actually estimate this guy. You can put question marks here. And you can also, given rest of the data, what would be the most likely observations here? Okay, and then fill those things in. Maybe since they only take two values, maybe the first one is 1, 1. Maybe it also takes 2, 1. Maybe with probability 0.5. Maybe with probability let's say 0.3, and maybe with probability 0.7. So you'll have for each of these guys you'll have two entries. Okay, 2 weights, and then you can complete this data this way and do MLE again, as if you have now fulfilled entries here, but with weights. So these guys will have weight 1, but these guys will split into 2 parts, 2 observations, and each one will have a weight. And the weight is computed as what is the likelihood, what is the probability that this guy, the missing number, could have been a 1? What is the probability that the missing number could have been a 2? Right? You can do that as well. So, I mean, this is related to your homework question. So that's what I'm kind of coming inside. I don't know if your homework question is it will be up after you finish the current one. And so just to kind of summarize, when there is structure in the inputs and outputs of a machine learning pipeline, you like to consider directed probability graphical models or undirected graphical models. And many of the methods, maybe not nonlinear methods or kernel methods, but many of the methods that you've seen, like linear regression, Naive-based classifier, and all the things that we saw today, like latent divisional allocation and variations of topic modeling, all these methods are essentially these guys, directed graphs and undirected graphs in disguise. Okay, they didn't explicitly say that they are the case when they started it, but that's what they are. So you can add variations to the LDA model, for example. Now you can add additional random variables which are related to some other metadata and actually make the LDA model even more complicated, right? I mean, based on your domain application. Maybe you just don't have documents, you also have documents and some meta information about the authors, some other information about something else. Then you can consider them as random variables and build a model which is part LDA and part something else. And those random variables are related to these random variables. And then you can do a full-fledged inference and learning. Okay, so that's how you would build a model in a principled way, not a very heuristic way of defining some rules for authors, defining some rules on topics, and somehow doing some ML task, right? I mean, you can do that as well, whichever works. But yeah, so that's it. So I think yeah.